The Lamb Jewish Library of Australia would like to thank you for attending tonight's talk with Professor Stephen Prawer on Jews and the Atom Bomb. My name is Lauren Joffe and I'm the Library Director. It is wonderful to see you all here tonight. On behalf of the Library Chairperson, Dr. Rolene Lamb, and everyone at the Library, I would like to extend a warm welcome to you all, and in particular to Stephen. Many of you will have attended our events before, but in case you have not, let me tell you a little bit about our library. We are a major Jewish information resource center with titles in English, Hebrew, and Yiddish. We have an extensive ebook and audiobook collection, which is very easy to use. The Write Your Story program has published over 140 memoirs, and we are probably the largest publisher of Holocaust memoirs in English in the world. We run an interesting program of events, including author talks, lectures, discussions, children's programs, and a book club. Since COVID-19, we have moved all our programs online. For information on upcoming events, please have a look at our new website, Facebook, or Instagram. We opened the library up again this week, and it was great to see so many of you in person again. Professor Prawer is no stranger to the library. In August, he presented a very well-received talk, which was both informative and interesting, on Jews and diamonds. In 2019, Professor Prawer also led an interesting discussion series at the library based on the books of the late Rabbi Lord Jonathan Sacks. Stephen Prawer is a professor of physics at the University of Melbourne. He has a worldwide reputation in advanced diamond science and technology, with over 30 years of experience and over 390 scientific publications. A particular focus has been the merging of the areas of nanoscience and neuroscience to push the boundaries of bionic devices. He has held numerous senior positions and has been the recipient of numerous awards. Stephen, we are honored to have you with us. After the conversation, Naomi will be one of our librarians, will pass on any questions that you may have for Stephen. Please add them to the chat box during the conversation. I would like to thank all the library staff who were involved in tonight's event: Joey, Hannah, Naomi, and Sophie. Stephen, over to you. Thank you.
Good evening, everybody. Tonight I would like to tell you a little bit about Jews and the atom bomb and about their contribution to the atom bomb and, strangely, the Nazis' contribution to the atom bomb. So we're going to do a little bit of a mix tonight of some physics and some history and some Holocaust history. Hopefully it will hang together for you and you'll start to understand the role of Jews in the development of nuclear weapons. So my first slide is a picture of the Trinity Test. This was a test of the atom bomb in July of 1945, prior to the real bombs being dropped on Hiroshima and Nagasaki. No one knew what the bomb was actually going to do. They set it up in the desert and they built this house. Can you all see my cursor, I hope? Is that a yes? Okay, great. So they set up this fake house. They put some dummies inside and then they set up some cameras to watch what was going to happen. So this was a picture from about 100 miles away, and this is what happened to this house. I think that this house was a few kilometers away from the blast center, completely obliterated the house. And the scientists who were there, they said that they had actually witnessed the finger of God. They were inspired by what they had managed to do over the last 2 years in the Manhattan Project, and that the science had actually worked. So this was a wonderful demonstration, if you call it wonderful, of the power of science In order to understand the power of the science, I'd like to take you back to Albert Einstein. Now, Albert Einstein was, and I have to stress here something very significant. Albert Einstein had no knowledge of nuclear weapons or nuclear forces. He was a man of thought, a man of thought experiments. He once envisaged as a young child holding a mirror in front of himself and asking what would happen if I ran at the speed of light. Would I still see my reflection in the mirror? In 1905, while he was working in the patent office, he came up with many revolutionary ideas, but the one I want to talk about here is the theory of relativity. And he started off, as Jews often do, with axioms or propositions. And he had two basic propositions that, if you think about it, are very, well, the first one is extremely reasonable, which is that the laws of physics should be the same for everybody. There should be no differentiation between the laws of physics if you're on a train, or you are in an elevator, or you are on the, or you're in your house, or you're in an aeroplane. If the laws of physics depends on where you are and how fast you're going, those laws aren't very useful at all. So think about any law that depends on your location isn't much use at all. We like to think of the laws of physics. In fact, we do think of the laws of physics as being universal, true everywhere in the universe. Now, of course, you can't prove that's the case, but it is certainly an assumption that we live by, that the rules of science are the same for everyone everywhere. And the second proposition that was much more revolutionary is that the speed of light is the same for everybody, no matter how fast they are going. Now, this idea was completely counterintuitive. For example, suppose that I am traveling towards another car. And if the car is traveling towards me at 60 kilometers an hour and I'm traveling towards it at 60 kilometers an hour, then I will measure the speed of that other car at 120 kilometers an hour. And that's what police cars do when they measure and clock your speed. But if I turn my car around and I travel in the other direction, then in fact, if I traveled at 60 kilometers an hour and the other car was traveling at 60 kilometers an hour, we would have no relative speed at all. But that's not what happens when people measure the actual speed of light. Counterintuitively, suppose that I've got a spaceship approaching the sun. And in this spaceship, we've got a couple of people who are busy measuring the speed of light. And let's suppose this spaceship is approaching the sun at half the speed of light, very, very, very fast. Well, these two people on the spaceship, if the spaceship was like a car traveling towards us, they would conclude, well, the speed of light coming out of the sun is c, that's the speed of light, very fast, but I'll tell you what that number is in a minute. I'm traveling at half the speed of light, so I should be measuring the speed of light coming out of the sun at 3/2 the speed of light. This is like the car traveling at 60 kilometers an hour, I'm traveling at 30 kilometers an hour, so I would measure the speed of the car approaching me at 90 kilometers an hour. And indeed, if I turned around, for example, and I was traveling at 60 kilometers an hour in this direction, and the speed of light we're going to put at 60 kilometers an hour, and this is 30 kilometers, I'm traveling at 30 kilometers an hour, well, then I would measure the speed of light as 30 kilometers an hour, slower. This is our common everyday experience. But that is not what light does. In fact, both of these observers in the spaceship will measure the speed of light to be exactly the same. This is counterintuitive, but in fact, it is absolutely true. And every experiment done in the last 150 years or 120 years has confirmed this experimental observation, that the speed of light is constant for everyone moving through, everyone measures the same speed of light, because the speed of light is not like other speeds, like a car can travel at 60 kilometers an hour or 100 kilometers an hour, but light always travels at exactly the same speed. And in fact, that speed is the fastest speed that anything can travel at. And if people are want me to stop and go back, please put up your hand or say something. I'm sure that I could go back and confirm this. So basically, this observation that the speed of light is the same for everybody had some astounding consequences. And if you want to work through those consequences, you'll have to come and do a little physics course, which I don't have time for tonight. But the consequences of this were absolutely astounding to the physics community. These two simple assumptions, that the speed of light is the same for everybody and the laws of physics are the same for everybody, had astounding consequences. So, you know, for most of us, when we think about people traveling at in different frames of reference, like in a jetliner, for example, although, of course, we know the people on the plane aren't in the same time zone, we don't expect our watches to travel, to click at a different rate on the plane than they do on the Earth. So in other words, if, for example, I go for a joyride, 12-hour joyride, and go around Antarctica and then come back to Melbourne, I expect my watch to still be synchronized with the watches of the people left in Melbourne. But that's just not what happens. In fact, by virtue of the fact that you are on the plane traveling at a speed that's not zero, your clocks will actually run slow. This is a remarkable fact, but in fact, it's been measured and confirmed many times. And if you don't take that into account, your global positioning system no longer works, because the satellites of the global positioning system are traveling fast. It depends on very precise timing. And if we didn't make corrections for relativity, those the global positioning system would, within a few days, be out by meters, tens of meters, hundreds of meters. So in fact, every time we, this is confirmed, moving clocks run slow. That's an incredible thought, that time is relative between different observers. And not only that, length is also relative. So for example, this soccer ball had a diameter of L. Once we observe the soccer ball traveling fast, it contracts in length. So clocks run slow and are no longer, the speed of a clock is no longer absolute. Length is no longer absolute. And not only mass is also not absolute. So again, if you take a kilogram of sugar on the plane, you don't expect it to weigh less or more by virtue of the fact that the plane is traveling at 1,000 kilometers an hour. But that's not true. Again, experiments tell us that as objects travel closer and closer to the speed of light, they get heavier. Actually, if you think about it, this is kind of a logical conclusion. Let's suppose that we try to add more and more energy to something. So you're in your car, you put your foot on the accelerator and the car speeds up. You put your foot even further down on the accelerator and the car speeds up some more. You're burning petrol and the energy from the petrol is going into making the car go faster and faster and faster. But if the speed of light is absolutely the maximum speed that anything can go at, as I add more and more and more energy, what's going to happen to that energy? I can't go faster and faster and faster. So we are going to get to a cosmic speed limit of the speed of light. And after that, any extra energy that we put into the system goes into increasing the mass of the object, not into increasing its speed, because we can't ever go faster than the speed of light. So Einstein, in one fell swoop, got rid of some of our most precious assumptions, which is clocks run the same rate for everybody, not true. Length is the same for everybody, not true. Mass is the same for everybody, not true. What is true is that the laws of physics are the same for everybody. So this was Einstein's logic. Takes about 5 lectures, undergraduate lectures, or even at BCE to go through the details of this, but I'm going to give you the conclusion. So those were really dramatic predictions. And in the 1905, when Einstein presented this work, there was very little experimental evidence to back him up. This was the conclusions he drew from making these 2 assumptions, which he believed were reasonable and were valid. And from those assumptions, these conclusions flowed. And in 1920 or so, he made a prediction about the position of certain stars, and those predictions came out to be exactly right, and he was catapulted into being the Pope of physics around the world, unquestionably the most famous scientist in the world. But in 1905, he had not yet got any experimental evidence. So the German reaction to this was incredible. The Germans objected deeply to his science. Now, it wasn't enough that they said he was a Jew who was doing physics. They actually concluded that that Einstein's physics was Jewish physics, an extraordinary notion. And this was not your rabble that introduced this. This was some of the most respected of German scientists at the time. So again, I want to try to stress the idea. Einstein had these thoughts, and he then told the scientific establishment, mass is relative, length is relative, time is relative. And people objected to this, right? Most of the world, once the evidence was in, was won over, but not the German physicists. So Leonard was a Nobel Prize winner in 1905, and originally he and Einstein were friendly, but later on, Leonard became a virulent anti-Semite, and he argued that to restore experimentalism to its proper place, we had to get rid of Jewish physics. And what did he mean by Jewish spirit? Well, what he wrote was as follows: the Jew conspicuously lacks any understanding of truth beyond a merely superficial agreement with reality, which is independent of human thought. This is in contrast to the Aryan science drive, which is as obstinate as is serious in its quest for truth. So what he was basically saying is that Einstein's physics was a mere construction, and its relationship to anything that was real or truthful was perverted. And in fact, another scientist, Theory, in 1937, had something quite profound to say, where he tried to explain what Jewish physics is and what Jewish thinking. So, and this, of course, is the opinion of an anti-Semite, but look at what they were doing in Germany at the time. So he says Einstein's theory is like Talmudic theory. So the task of the Talmud is to fulfill the precepts of the Torah by circumventing them. So, for example, and he gets this wrong, but you'll see the reference to what we, about an Eruv. The Talmudic Jew who places a food basket under his seat in a railway car, thus turning it formally into his residence, and obeying, therefore, formally the law that on the Sabbath one should not travel more than a mile from his residence. It is this formal fulfillment that is important for the Jew. A criticism of halakha that many of us might, in fact, be somewhat sympathetic to. The idea that, you know, we do a fake sale of chametz, and, you know, we do all these things with the halakha, but he was going further. He wasn't actually concerned about criticizing the Talmudic halachic law. He says it manifests itself in Jewish physics. So he says the theory of relativity, the principle of the constancy of the speed of light, represents the Torah, which under all circumstances must be fulfilled. So what he's saying is, in halakha, we have a set of principles, and we have to fulfill those principles, even though we do something like this in order to be able to formally be able to say that we have acquitted our responsibilities under the halakha. He says the same is true. Einstein came up with a biblical law. Speed of light is constant, and then he builds a, like this, in order to be able to fulfill that requirement, right? So you can read this yourselves. The notion of space and time are deprived of all spirit and defined in an expedient, purely intellectual way. So what he's saying is, Einstein, you've created a Jewish physics. It's like a Talmud. It's like a sukkah that you say has got walls, but it's really just a mesh, right? And so he was accusing Einstein of fantasy, of intellectual sophisticy, and basically the Germans. It wasn't enough that the Germans didn't like the Jews, they also didn't like Jewish physics, accusing it of being a distortion, a perversion of real German physics, which was experiment experiment and then theory to back the experiment. Now, Einstein, of course, had had nothing to say here, because if anyone in the whole world was actually after the truth, the profound truth, it would have been Einstein. So that was in 1937, 5 years after this horrible law had been put out in Germany, the law for the restoration of civil service. At this stage, the Nazis were still into euphemisms. So it was enacted in 1933, and although at the beginning was a little unclear, etc., basically what it basically said is Jews can't be civil servants, and in Germany, all professors at universities are civil servants. So overnight, Jews could be dismissed from their posts or forced into retirement without pensions. The only exception to this, because of the German chancellor at the time, prior to Hitler becoming the chancellor, was the Jews who had either served in the war or whose fathers had served in the war and were killed in the war, were given a reprieve from this, which was removed the next year. So Jews, some who saw the writing on the wall, left. They were kicked out of their positions, and basically by this law, they threw away their hard-won scientific supremacy. You know, when the Technion was established in Israel in 1920s, there was a virulent argument about what the language of instruction should be. And in the end, they insisted that the people who were founding the Technion said, well, how could we possibly have a language of instruction anything but German? Because German is the language of science and physics and maths, etc. supreme was German scientists at the time. I mean, the Technion won the argument, or the purists won the argument, and they made Hebrew the language of instruction, but it was touch and go. In 1933, seeing these list of people, some of whom I will mention, is basically all the people that understood nuclear physics left at that stage, and many of them ended up in the United States. And this is a picture from 1933. Einstein returned briefly to Belgium, renounced his German citizenship prior to leaving Europe forever, never came back. And this is a German cartoon showing Einstein being kicked out and good riddance to him. By this stage, as I said, Einstein was the most famous scientist in the world, the most recognized face in the world. And Hitler was warned that, that Germany's science had been depleted to the point at which it no longer was operational. And his reaction was, if the dismissal of the Jews means the end of German science, then we will do without science for a few years. So this law of the restoration of civil service depleted Germany of its ability to actually make an atom bomb, is one of my conclusions. They were so preoccupied with killing Jews that they couldn't even think about why Jews could be useful to them in a purely exploitative fashion. Okay, so now I want to fast forward to, well, the 1930s, where people started thinking about whether or not we could get weapons out of these new theories that were evolving. So a little bit of physics here. You know, if I have a golf ball that's just on the tee, it doesn't have any kinetic energy. Kinetic just means moving energy. And when I hit the golf ball, it starts to move, and you know that that golf ball has energy. If it hits a window, it'll break the window. If it hits my head, it'll hurt my head. More energy, you can have an idea of a bullet inside a gun. The gunpowder explodes, pushes the bullet out, and that bullet obviously has a lot of kinetic energy, and that kinetic energy can do a lot of damage to a person if it hits that person. And the energy is given by this very simple formula, half mv squared. V is the velocity or the speed. So this is an important formula. It says that if you go twice as fast, you have 4 times more energy. So for example, if you're traveling at 120 kilometers an hour, you need 4 times more distance to stop as compared to 60 kilometers an hour. If you're in people think that traveling a 60 kilometer hour in a 50 kilometer zone is no big deal, but in fact, it takes you 30% more time to stop. And if you hit someone, you're hitting them with 30% more energy. So that square there is important, right? Double the speed, quadruple the amount of energy you've got. Well, we know that there's a max. So this would be the reaction to the, this would be the formula that would apply if we didn't have Einstein's relativity, because Einstein, according to non-relativists, you could just continue to increase the speed. But we know that the speed of light is the maximum speed. So as you are adding more and more energy to the system, you are in fact getting closer and closer to the speed of light, but you'll never get there. And the amount of energy that you can then get when the mass does get turned into energy is given by Einstein's famous formula, E equals mc squared. Now I have to add, when Einstein did this formula, he in fact used the classical laws of physics, the same laws of physics where you get a half mv squared. He used his 2 principles of the constancy of the speed of light and the fact that the laws of physics are the same in for everybody to get this formula. It had nothing to do with bombs, power, energy, etc. It was purely a consequence of his advanced thinking. But by the 1930s, people started to think about whether or not this formula could actually be useful. So I want to give you a little numerical example to give you some flavor for how much energy is involved in this. So consider a single grain of rice, long grain rice. It weighs about 30 milligrams, which is, you know, pretty much the weight of a little tablet that you take. I have to take my Lipitor every day, about 30 milligrams of Lipitor for cholesterol. So how much energy is there in that grain of rice? Well, let's apply E equals mc squared. So the mass has to be expressed in kilograms. So it's 0.03 grams, but there are 1,000 grams of a kilogram. So it's only a 300,000th of a kilogram, this 1 grain of rice. The speed of light is huge, 300 million meters per second. We have to multiply it twice, and you get this enormous number. This 10 to the 12 just means I should be putting 12 zeros here. I couldn't bother writing them out. So how much energy is that? Well, if you, like me, considering putting solar cells on your roof, you might be interested in how much energy you use every day. So I use in my house about 25 kilowatt hours. I've got kids who don't turn off the lights. Should be less than that, but it's on average 25 kilowatt hours. And that's about 90 million joules. If you get your gas bill is not expressed in kilowatt hours. Your gas bill is expressed in terms of megajoules. So this would be 90 megajoules per day that I'm using. And so that's how much I use in one day. If I take this number and divide it by this number, I can tell you that I can power my house for 30,000 days or 82 years from 1 grain of rice, right? So that's an incredible amount of energy if I could learn how to turn that grain of rice into pure energy. And if you might have read books like Demons, Angels and Demons, there's many of the books talk about the amount of energy that can be liberated by combining matter and antimatter and creating pure energy. We'll get to that at the very end of the talk. That's not science fiction, that's real. But anyway, just to give you this idea of this enormous amount of energy that's available in 1 grain of rice. So how can we extract all that energy from a grain of rice? Well, we don't know any way of doing that, but we can extract some of the energy from masses under special circumstances. And by 1930, many of the Jewish scientists who had left Germany were realizing that they could split the atom and release huge amounts of energy. So how does this work? Well, basically it works like this. A particle comes into an atom and splits it in two. Now, when it splits, it releases energy. The simple idea here is that if, for example, this original nucleus weighed 100 units, after it's split, it splits into one thing that is 30 units and another one that is 60 units. 10 units of mass are missing, and that 10 units of mass that are missing is turned into energy, E equals mc squared. And we know that although the amount of the atom is very light, but this number is so huge that we get an enormous amount of energy from this process. So that's one element. The other element is that you need a chain reaction to make a bomb. You need this atom to split and create a chain reaction that will cause other atoms to split and release their energy. And this little YouTube video is probably as good as any at showing you what this chain reaction looks like. Can you all see the video? Hello? Rolling, can you see the video?
Yeah, it's just loading.
Okay, great. All right, so here is a ping pong ball on a mousetrap. And if you drop a ping pong ball on it, the mousetrap goes off, right? Now, someone has set up here thousands of mousetraps, each one of which is nice. So we can have a look at that in slow motion. All right, so hopefully you get the idea, right, of one ball disintegrating and causing others to disintegrate, and within a very, very short period of time, you get an intense explosion. So this was starting to be realized in the mid-1930s by some of the people, some of the key people in these stories, all of them Jews. So Albert Einstein first came up with the idea of E = mc squared. I'll tell you about his letter to President Roosevelt in a second. Leo Szilard helped build the first nuclear reactor, and in fact helped Einstein write the letter to President Roosevelt. Niels Bohr, who was the father of atomic theory, exiled to Denmark and then to the US, and some of you might have seen the play Copenhagen, which talks about the meeting between Bohr and Heisenberg. Heisenberg was in Germany at the time. Bohr and Heisenberg sort of circled around each other, Bohr trying to find out whether Heisenberg was trying to build a bomb and Heisenberg trying to do the same thing with Bohr. So by the 1930s, Einstein, who remember had only thought about pure thought experiments, nothing about bombs, nothing about nuclear energy, but he was convinced that now was the time to alert the US president of the possibility, and you can see here in the course of the last 4 months, it has been made probable through the work of Fermi and in America that it may become possible to set up a nuclear chain reaction in a large mass of uranium by which vast amounts of power and large quantities of radium-like elements would be generated. Now it appears almost certainly that this could be achieved in the immediate future. This new phenomenon would also lead to the constructions of bombs. So, and he goes on in this letter to tell the president that the United States really needed to do something about Germany acquiring enough uranium to be able to make a bomb. And Roosevelt took this letter pretty seriously and started a process by which the US would look into whether or not uranium could be turned into a bomb. So other people who came in and made contributions. So my father really loved the fact that Max Born was Olivia Newton-John's grandfather. So if he really liked Olivia Newton-John. He used to say to my mother, she can put her slippers under my bed anytime she likes. And to which my mother would retort, yeah, and Robert Redford, he can put his slippers under my bed anytime he likes. Lise Maitner was a fascinating lady. She was she discovered this process of fission. Shouldn't have won the Nobel Prize, but like so many women in her time, was in fact shoehorned and ignored. Shameful history, but she was the first one to recognize the idea of fission. Enrico Fermi wasn't Jewish, but he married a Jewish woman and he left fascist Italy to join the United States. And he was the person who constructed the first nuclear reactor in a squash court in Chicago. And here are some other players that names you might know. Robert Oppenheimer was born in America. He was the director of the Manhattan Project, and he was the one responsible for the first atomic bomb. He was very supportive of the first atomic bomb, but he thought that the dropping of the bomb on Nagasaki was unnecessary. He went to see President Truman afterwards and said, "I feel like I've got blood on my hands." Truman responded that he was a crybaby and ordered that he never meet with him again. Edward Teller, you might know him. He is the model for Dr. Strangelove in the movie. I don't know if the movie's called Dr. Strangelove, but he was the exotic scientist. He remained committed to the idea of using nuclear weapons as a deterrent. He invented the H-bomb, which was 1,000 times more powerful than the atom bomb. And of course, Shimon Peres, who was the founder of Israel's nuclear program. So Einstein, if I go back to Einstein's letter, he says down here, however, such bombs might very well prove to be too heavy for transportation by air. So when Einstein wrote his letter, it wasn't clear that making a bomb was practical. It was probably the bomb, according to technology at the time, the bomb might have to be 400 kilos, 1,000 kilos. And at that stage, people didn't believe that they could put it in a plane and drop that bomb. But in Birmingham, two more Jews, Frisch and Pearls, did some calculations, and they concluded that, in fact, they could make a bomb with only 50 kilograms of uranium. And they already knew exactly what this bomb would do. It would explode and provide at least 1,000 tons of dynamite, tons, not kilograms, tons. And the energy would be liberated in a small volume, and the temperature would be like the temperature of the sun. And they knew that it would kill a lot of people, and some of the radioactivity will be carried along with the wind and will spread the contamination. So this really exercised the attention of the authorities, and they made the trip from England to the US, where the Americans had set up the Manhattan Project. So just to explain, actually an atom bomb is probably a pretty simple device in a sense. It consists of two bits of uranium, which in their separate forms are below critical mass. I should just explain, the critical mass is the mass that you need in order for the chain reaction to occur. If the mass of uranium is too small, those little particles that are produced every time there's a separation, every time there's a fission event, every time you split the atom, they just escape. But if it's big enough, they can't escape, and one neutron will hit another atom, and you get the chain reaction that I showed you before. It's like if I put my mousetraps far apart, then if they were, a big distance apart, then throwing in one ball would maybe set off one mousetrap, but it wouldn't set off the whole chain reaction. So these two pieces of uranium separated from each other are pretty safe, but when the bomb is dropped, a conventional explosive forces this piece of uranium into this piece of uranium, and it reaches critical mass and it explodes. And in this bomb, there are about 50 kilograms of uranium. Now, the thing is that that it's very difficult to. You might have heard of the Iranians trying to produce enough uranium for a bomb. So when you dig up uranium out of the ground, it is an isotope of uranium called uranium-238, which is radioactive but cannot be turned into a bomb. The only part of the uranium that can be turned into a bomb is uranium-235, which is only about 1% of the uranium. So what you have to do in order to create a bomb is you have to purify the uranium, making it more and more 235 and less 238. The trouble is that these two things are really hard to separate. really, really hard to separate. And at Los Alamos, they built these huge race rings to basically accelerate the uranium atom by atom to separate out the heavier U-238 from the lighter U-235. This is a picture of the people, of the ladies of the collutron, each sitting at a panel. Their job was to keep on adjusting all the dials to keep the maximum current. In those days, they didn't have computers to do this sort of control, so they were just twiddling the dials, keeping the current maximum. They had no idea what they were doing. They were just, that was their instructions: keep the maximum current, keep twiddling and adjusting the dials. Atom by atom, they purified the U-238 until they had enough uranium-235 to make this bomb. Now, I couldn't resist showing you this little website. Is it coming up?
Yeah, it'll come up in 1 sec.
So if we put in Melbourne, which I can put in any city I like, but should we put in Melbourne or should we put in Tel Aviv or Jerusalem? Let me put in Jerusalem. Oops. Oh, fat fingers. Okay. So here is Jerusalem. At least I thought it was. No, I've mistyped it. 1 second. Jerusalem. I got it right now. Okay, here is Jerusalem, and let's drop a atom bomb on Jerusalem. Let's drop the Hiroshima bomb on Jerusalem, which is the smallest weapon that's been. And let's see what happens. So we detonate the bomb. Here are the expected number of casualties in this area, and you can see the bomb blast. You can see it would destroy and kill nearly 100,000 people and injure 250,000 people in a radius from the Vaseret Zion all the way to Mea Sharim. And you can see here the enormous destruction. And this is one of the very, very smallest bombs. So if you, for example, take one of the North Korean bombs and do it, then you can see today what could be done with even a fairly primitive North Korean bomb. And I say this in order for people to understand why, in fact, the Iranian threat is so horrendous. Just to give you some idea, even if they had a very, very small weapon, they could wipe out a tenth of Jerusalem's population, of course, make this whole area uninhabitable for the foreseeable future. And they would not have to do anything more than repeat the Hiroshima bomb, a technology that is over 70 years old now. So just to stress that again. So after the war, a lot of the Jews were very, very upset at what they had done. The Jews joined the effort to build a bomb because of their fear of Nazism. And even Einstein realized that pacifism was not the appropriate response to the prospect that if Hitler would get the bomb first and win the war, what would happen to the whole world? So, but after Germany was defeated, as you know, the bomb wasn't ready to be used on Germany, and it was used then on Japan. And Oppenheimer and many of the Jews who were involved were very opposed. Oppenheimer was relatively agreed that there was a case to drop the bomb on Hiroshima, but he was dead against dropping it on Nagasaki. He thought that was really a war crime and inappropriate. And after the war, he increasingly became ostracized from the American establishment, and he was accused of being a communist, and he was in fact vilified and removed from his position, as many of the other Jews were as well who worked on the bomb. One of the most famous of those is Joseph Rotblatt, who left the Manhattan Project in 1944 once Germany had been defeated, and he founded the anti-war movement with support from Einstein, Bertrand Russell, supported the Nuclear Non-Proliferation Treaty, and you might have heard about the Pugwash Conferences on Science and World Affairs, and he won the Nobel Prize in 1995 for his work. I think in 1999, he wrote a Hippocratic Oath for scientists, and he wasn't particularly advocating a particular language, but you can see here what he is saying. I promise to work for a better world where science and technology are used in socially responsible ways. I will not use my education for any purposes intended to harm human beings or the environment. Throughout my career, I'll consider the ethical implications of my work before I take action. While the demands placed upon me might be great, I sign this declaration because I recognize that individual responsibility is the first step on the path to peace. So when Richard Feynman was asked, why did you not think about what you were doing as you were developing the bomb? He was honest. He said, the science was so overwhelming. It was such an elixir to be in an environment where no expense was too much, where the greatest minds of the world were all focused on one goal, to build this atomic bomb. We got carried away. We didn't think about the ethical consequences of what we were doing. It was just the excitement of the science was just too great. Not everyone felt that way, but many, many of them did. So, there are a lot of comments. I'll conclude with some thoughts about this ethical question: can deterrence via deadly weapons really promote pikuach nefesh, the sanctity of life, in a moment? But I just want to conclude this part, which basically to tell you that Jews were heavily involved at all stages in the development of atomic and nuclear physics. This law for the restoration of the civil service, this euphemistic law, caused most Germans who could have helped create a German bomb to emigrate. It motivated the Jewish emigres to work on the bomb, and it also convinced the US to engage the largest, most concentrated scientific development in history, so the Nazis don't blow us up, in Roosevelt words. The Jews who were involved generally did not support dropping the bomb on Japan, and particularly not on Nagasaki. And once the Nazis were defeated, many Jews became prominent in the movement for the peaceful use of nuclear technology. So I'm nearly done, but before I go, two more things. One of them is this question of deterrence. Many years ago in Israel, I was listening to a talk that tried to explain why Truman dropped the bomb on Japan. So of course, this was a very controversial decision. Some people could accuse him of a war crime. But in the time in 1945, the Japanese were fighting to the last drop of blood in the Pacific. And there were two camps apparently in Japan. One of them said, the war is lost, let us retain what we can from our situation and let's end this. But there was another group madly loyal to the emperor who said, our responsibility now is not to win. It's not even to stay alive. It's to preserve our honor and our dignity. And it was like two samurais approaching each other. If two samurais approach each other on the field of battle, the worst that can happen to one of the samurais is not that they get killed, it's that they are dishonored, that they die a dishonorable death. And so it doesn't matter that the samurai is going out knowing that he'll be killed, as long as he does it with honor, it's not the worst outcome. But there's no honor in a samurai coming out to fight a tank, right? Because we're not talking anymore about, not talking about retaining your honor. There's no possibility of being able to defeat a tank. And what this Israeli academic was suggesting is, that the atom bomb gave Japan the permission to surrender. It made it possible for them to surrender with honor, in the sense that the victory was totally impossible, not improbable, not costly, but impossible. And in the face of overwhelming, truly overwhelming odds, there was no dishonor in surrendering. His comment was, the atom bomb that Israel has, or doesn't have, depending on your point of view, has the same function. So he said Egypt and Jordan and other places can sue for peace with Israel because Israel has the bomb, and therefore destroying Israel is no longer a possibility. So because it's no longer a possibility to defeat Israel to wipe it off the face of the earth militarily, there's no dishonor in brokering a peace. It's an interesting hypothesis, and I will leave it to you to think about whether deterrence can really quote pikuach nefesh. I will say one other thing, in my opinion, and this is just my personal opinion, the rise of technology has actually made war far less deadly than it's ever been. So precision munitions, etc. If you think about the Rwandan massacre, 1 million people were killed with machetes, right? Today, with precision weapons, for all of the collateral damage that occurs, the more mechanized an army, the more automated an army, the less collateral damages, the less death there is. And you can actually see that, you know, World War I, I don't know how many people were killed. Far, far less people are killed today in conflicts than have ever been in the past. That's my personal opinion. I do believe in working for a better world. I don't believe that it is necessarily the case that working for military, in military context, is not necessarily working for a better world. I think there is a strong role of deterrence. But I just want to end up on talking about something that is a little bit more positive to end up on. So I've told you about the amazingly destructive forces of nuclear particles, etc. And I said, you know, I can't take my grain of rice and turn it into energy, pure energy. We don't know how to do that. But we do know how to do that on a subatomic level. So there are things called positrons, which are basically electrons that have a positive charge. And when a positron meets an electron, they annihilate each other. One of them is matter, the electron, the other one is antimatter, a positron. And when they meet each other, they totally annihilate in a burst of light, and 2 gamma rays are emitted. And this is not rocket science. Well, it is rocket science, but it's at the Alfred Hospital. In the Alfred Hospital is a machine that smashes atoms to produce these positrons. The positrons are collected and they're injected into the body of patients. And here you see a patient lying on the table about to have a PET scan. When the positrons are emitted into the brain, for example, of the person, the positrons are attracted to the regions of the brain where there's high metabolic rate, lots of blood flowing. There they meet an electron and they annihilate. And the person is put into this detector here. You can see this detector. And because the 2 gamma rays are emitted at exactly the same time, then this detector, when you get a click here and you get a click here, you know that this positron was located at this spot here. And then you get a click here and a click here, and you start to form these lines, and then the patient moves through the positron emission tomography analysis chamber, and eventually you get pictures like this. So this is amazing. This is a picture of a person's brain, and they've got these positron emission tomography. And this is a healthy person, and you ask the person to do certain things. So when they look at something, you can see this part of the brain light up. That's called the visual cortex. And they listen, and this is the auditory cortex. And if you ask them to think, I don't know what would happen if many of the kids today were asked to do this, but nevertheless, here, the front part of the brain is operational, the frontal cortex. And interestingly, when you're asked to remember, see how much the back of the brain lights up. This is because memories are often very visual. And when you're working, not very much activity at all in the brain. So you can see inside with what someone's thinking and doing by this amazing new technique. But if you look, for example, at trying to diagnose Alzheimer's, well, Alzheimer's is the death of many cells in the body, cells in the brain, and you can see here the red is where there is brain activity, and the blue is where there's no brain activity. And so, someone that has bad Alzheimer's disease, you can see here, so much of the brain is no longer alive. It can also be used to find different tumors. You can see here, this person has a tumor that's grown in this region here, and so that you don't have to do biopsies. You can give the person this PET scan, and you can see the shrinking or the growing of tumors. So this is an example of how this technology has been used for the good rather than for destruction. And of course, we have nuclear power, which is a wonderful, wonderful source of clean energy. Again, remember my grain of rice. So with that, I will conclude, just to come back to my conclusion slide and just remind you, yes, Jews have been heavily involved in this, in nuclear technology. The Nazis provided both the motivation and the means, and had they not eliminated the Jews and sent them away, it may well be that they would have won the war. So perhaps in a strange, strange way, we can be grateful for those laws that sent so many Jews out of the country so early on. Okay, I'll stop there. Thank you very much all for listening. I hope that wasn't too long, and happy to take questions now.
Thanks, Stephen. Sorry, we'll just fix that. It's such an interesting topic, but we've really only got time for one question, I think. We've been asked, how do you, why do you think that the US did not turn to Einstein in the development of their own atomic weapons?
Well, by the time, well, I should say Einstein wanted nothing to do with the development of the bomb. He was forced into using his prestige in order to convince Roosevelt to read the letter. But the truth is that he played no part in the Manhattan Project, and he did not want to play any part in the Manhattan Project. So by that stage, he was the elder man of physics. He didn't actually have all that much to offer for what was essentially a huge engineering problem of figuring out how to refine U-235 from U-238. So it wasn't his, he was past it to some extent by that stage. Is that, oh, okay. What is injected?
Probably all we've got time for. I'll hand over now to Lauren, the Lamb Library Director.
Okay.
Thank you very much, Stephen, for such an informative and fascinating talk. You have a way of explaining such complex ideas in an understandable way. We really appreciate you giving so generously of your time and sharing your knowledge with us, and we look forward to future talks with you. Before we end tonight, I'd like to remind you all we've got an author talk next Wednesday with Dr. Harry Liu about his new book, Patterson of Israel, and he will be interviewed by Barry Rogers, OAM. And I'd also like to mention that on November the 29th, the library has its annual fundraising appeal. As we rely on the community for funding, we would appreciate your support. Thank you all so much for attending tonight, and a big thank you again to Stephen. Thank you very much. Good night, everybody.